In this video, I'll show you how to solve the ALEKS problem called calculating key distances in the BCC unit cell. So first of all, I want you to make sure that you are not trying to solve the FCC unit cell problem. That problem looks almost exactly the same as this one. I do have a separate video if you're trying to solve the FCC unit cell problem. The strategy that we use for solving the BCC and the FCC unit cells, totally different. So if you're trying to solve the FCC unit cell problem, please don't watch this video. The answer that you're going to get is going to be wrong. Here is the BCC unit cell. We've got 3 of the corners highlighted, red, green, and blue. ALEKS is giving us the distance between 2 of those corners, and it's asking us to calculate the distance between 2 other corners. The relationship between these three corners is a right triangle. Even though it may not look like it in your particular cube, it definitely is. So we're going to be using the Pythagorean theorem to help us solve this problem. And I want you to begin by just sketching out a right triangle that resembles something like that. You are going to recognize that there are 3 corners of this triangle, and those 3 corners correspond to the 3 different balls at the corners of this cube. It is super, super important that you get these corners matched up correctly with the corners of the triangle. Otherwise, this problem is going to not work for you. So we've got 3 different distance relationships in this FCC or in the BCC unit cell. We've got this relationship with 2 spheres that are sharing an edge of the cube. And that distance or that relationship is going to be represented by the short side of your triangle right there. So this distance right here is this guy right here. You've got a distance between 2 spheres that spans across the face diagonally. It spans diagonally across the face of your unit cell, and that's going to be this length of the triangle right here. And then you also have a relationship between 2 spheres that spans through the center of your unit cell. That's a long distance. And that's going to be represented by this portion of the triangle. So seeing those relationships right there, what I want you to do is match the positions of these spheres, match them up with the corners of the triangle. So again, the short side, that's corresponding to the edge of the sphere. And for me, the edge of the sphere is a red corner and a green corner, but take your time and make sure that you're putting the red corner and the green corner in the right spot. Like for me, it would be wrong if I put the green corner in this particular position and I put the red corner in this particular position. And the reason I know that it's wrong is because this length right here is the length that spans through the center of the cube. The length that spans through the center of the cube is a relationship between the red sphere, not the green sphere. The red sphere spans through the center of the cube, connects to the blue one on the other side. So again, take your time to make sure that you get these spheres in the right spot. We have the green and the blue, which spans diagonally across the face. That's this side of the triangle. The red and the green on the short side of the triangle. And then the distance that goes through the center of the cube, that's the long side of the triangle. Your colors may not match up with mine, but make sure you get everything in the right spot. So we're going to be using the Pythagorean theorem to solve this problem. The side lengths are A, B, and C in terms of the Pythagorean theorem. What I want you to recognize, and I'm not really going to walk through a long derivation of this, the side length B is equal to the square root of 2a squared, or maybe it would be less crazy if I wrote I'm just going to leave it like that, 2a squared. So the side length B is, if we want to solve it in terms of A, side length B is the square root of 2a squared. And that, I'm not going to spend a lot of time on that, but that comes from the relationship that we would get on this face of the triangle. So if we're looking at this face of the triangle, if we say this is side length A, this is side length B, this is side length C, we could use the Pythagorean theorem for that as well. However, on this side, these 2 edges are exactly the same, so we could write that as A, and this would be our C. Using the Pythagorean theorem, a squared plus a squared equals c squared, or 2a squared equals c squared, or the square root of 2a squared equals c. Whew, that's a lot. And this distance here is what we're calling this side of the triangle. So this length here, in terms of A, is equal to 2a squared. Okay, so ALEKS is going to give us one of these distances. Again, for me, I got this distance right here, the red and the green. And because I know this distance, I also know this distance as well, because this distance I'm able to calculate if I know what A is. And it's asking me to calculate this distance right here between the red and the blue. So I'm going to do that again using Pythagorean theorem. A squared plus B squared equals C squared. However, instead of writing B squared, I'm going to write it in terms of A. So A squared plus the square root of 2A squared equals C squared. I'm going to do some algebra here. A squared plus the square root of 2A squared, oh my gosh, I feel like I've made this harder than it needs to be. The square root of 2A squared is 2A squared. This is a tongue twister. That's equal to C squared. I can combine these terms, 3A squared equals C squared, and then I can come up with whatever relationship is necessary for me in the problem. So since I have A and I'm being asked to solve for C, this equation is going to work out perfectly for me because I've got that C variable isolated. If the problem was flipped around the other direction, and if I knew C and I was trying to solve for A, then I would probably simplify a little bit further to isolate that A variable. You could also simplify it even further by taking care of the square root stuff, but I'm not, or the squaring, but I'm not going to do that yet. I'm going to plug some numbers in first. So I know my red and green length, which is 0.65. I'm going to plug that in as my value of A, 0.65, and that is equal to C squared. And then I'm going to let my calculator take care of the rest of it. So this is a little bit heavy on the algebra, but I know that you guys can work your way through this. I think the most important thing with this problem is that you take your time to build that triangle correctly, making sure that you're getting the spheres matched up in exactly the right spot. Because as you can imagine, if you don't get these spheres in the right spot, you're not going to end up solving the problem correctly. To two significant figures for me, that's going to be 1.4, and my unit, left the unit off to make it easier to look at, is nanometers.